Hi, how many of you have a camera when you take a photo, it does autofocus on the face? All right, there's a lot of people that raise their hands, and some of you might not even know that you have a camera that does that. What that means is that's facial recognition or computer vision. That also is a type of deep learning. And what's behind it is a neural net. Neural networks, many of you may have heard about them before, and if you have, you might also see them as being extremely complex topics. They're almost like, oh my God, what is that? That seems almost inapproachable. If you do know about them, then this talk might not necessarily be something you want to listen through, but I wanted to take neural nets and make them a little bit more approachable. I wanted to give you something that would feel less sort of mystery and complex. So my name is Melanie Warrick. I'm a data scientist and an engineer, and I am here to talk to you about neural nets for newbies. And specifically, I'm going to try to go through a little bit of a backstory, a little bit of history on neural networks. I want to spend some time giving you some fundamentals around the math and the structure. I also want to do a brief reference to the importance of systems engineering in particular. And I'm going to show you a little bit of code, talk a little bit about deep learning, and then give you some references where you can continue to do further research. My main goal with this talk, if you don't know about neural nets, I don't expect you to understand everything I'm going to cover, but I want you to be able to have a framework, something that you can start to build off of in terms of what neural nets are so that you can go on and further research them yourselves and find ways to apply them. Artificial neural nets. This idea has been around for a while, and what it is that we are trying to mimic or model the brain with our computers, in essence. In our brains, we have neurons connected with synapses, and those neurons will fire and send out signals across synapses. That's a little bit at a very abstract level of what's going on in your brain, and the neural net structure is trying to some degree, model that. But what is it at a very high level? It's an algorithm. And last year I talked about what machine learning is. And machine learning is a set of algorithms that do classification and prediction. And neural networks fall underneath that umbrella. So, as I mentioned, it was originally, the idea originally came about, let's try to take the brain structure and mimic that in our technology. And this is dated back to when computers really started to come of age in the 50s. But our computational power was extremely limited. The amount of data we were able to process, the amount of memory, and how much we could store in memory was extremely limited in comparison to now. I know most of us know about Moore's Law and how much exponentially we've seen the improvements in our capabilities with computers in even just the last decade. So in the 50s, when we were like, let's put our brain structure into a computer, there was a lot of excitement, a lot of hype. There was like, oh my God, we're going to have these robots now that act like us. And even with the more realistic expectations or pseudo-realistic expectations, we still just had so much limitations. We couldn't achieve what we wanted to with neural networks. In the last decade or so, we've started to see some actual value. And the areas in which we are seeing that value is in areas like natural language processing, speech recognition, things like computer vision and robotics. I'm sure all of us have heard, or many of us have heard about the cars that drive themselves and how that's going to replace all of our cars in the near future. Recommender systems, recommender engines in particular, where you're seeing some real value out there in the commercial space. If you've heard about the Netflix prize out of Kaggle, Kaggle's a competition site for data science. And there was a Netflix competition, and the winner of that actually used a neural net. So a lot of recommender engines are using neural nets. So are a lot of ad placement solutions, or at least I couldn't get anybody to verify it for me, but I have no doubt some of the bigger names out there are exploring it. And the reason why is because in these types of spaces in particular, where we have some very rich data, we are seeing that with more data, we can actually increase the accuracy of the results of our models. And this is where we also see other machine learning algorithms tapping out. Now, I really want to stress something here. Don't look at this and think, oh my God, neural nets will solve all my problems. They're good for certain types of problems. Those problems I mentioned in particular where you have very rich data sets, especially around images, around words and speech patterns. That's where you're going to see benefits like this. Not necessarily all data sets, not necessarily all problems. But yes, we have so much more data now that we've captured in those spaces, we're seeing neural nets really take off. Okay, you're like, okay, great. It's applied to speech recognition, it's this algorithm, but what does that mean? This is where we're going to start getting into math. And if you're rolling your eyes, let me just say this, you kind of have to get over it. Because if you really want to get serious about applying a neural net, you're going to have to understand the math. So before I show you a neural net and the math behind it, I want to just sort of level set us on taking an equation, and specifically in machine learning, one of the simplest equations is linear regression. Now, I'm not going to argue about like how valid this line is and so forth. I'm just trying to get us all on the same page in terms of the fact that in linear regression, you have a template algorithm. I'm sure all of us know this, or most of us know this, y equals mx plus b. And what you're trying to do with this data set is fit the line to the data with as little error as possible. And you won't start out typically knowing what that line is initially, but you'll start out with a line and you'll continue to tweak it and keep checking the error until it gets to the best solution you can come up with. And the way you tweak it is by continually shifting those coefficients. Your coefficients are the slope and the intercept. So you're just tweaking them, just wiggling them a little bit here and there and continually shifting that line and hopefully getting to a place where the error is as best as you can get. Keep that idea in mind as I start to go through neural nets. Now, for a neural net, the equation will start out in the neuron. As I mentioned before, we're modeling loosely the brain structure. And you have neurons in your brain. And in a neural net, we'll have one neuron, and there's an equation in that neuron. And it's taking a set of inputs. It's multiplying weights to that input, or those inputs. Those weights are your coefficients. So just remember that. You multiply the weights, you sum that data together, and then you're going to apply an activation function. Now, there's a number of different types of activation functions you can use, and it just depends on the problem you're solving. And I've listed a few examples up there. But the activation function is really just a way to transform the data and determine whether this neuron is going to send a signal. Is it going to fire? Is it passing anything on? So inputs times the coefficients, applying the activation function, and then maybe I'm sending on data, maybe I'm not. Now, that's great, that's abstract, but let's try to give you at least a sense of what that means with a more realistic example. This is all extremely simplified, just trying to give you at least a sense of how to start approaching it. But let's say you're trying to decide, am I going to go see a talk? And so you have a set of inputs. Those inputs are going to be binary. You're trying to decide, based on the speaker, like, do you like them or not? Is it a topic you're interested in or not? Is the timing good for you or not? And in this case, the speaker you don't know anything about, so it's a 0. The topic is something you really want to hear about, because it's like how to, have lightning speed response rate on something, I don't know. But it's a topic you're like, yes, I need to hear that. So that's a 1. And the timing, it's right after lunch, you want to take a nap, so it's a 0. You multiply those values times how important these different inputs are to you. And the topic is more important to you than the timing. So it's got a level of 50, or it's got a priority of 50%. That's your weight. You'll multiply them, add them together, and based on your threshold, and I'm loosely kind of doing the activation function in this case, but based on your threshold, you'll probably go to this talk. So you will send a signal from this neuron to say, yes, go to this talk. Again, I've very much oversimplified how this equation works. I'm just trying to give you the fundamentals on understanding how this equation is working inside of a neuron so you can further investigate in more detail neurons and how they work. As I mentioned, this is a processing unit. And when you're doing neural nets, you can have just one neuron, but typically you're going to have more than just one. And you're going to have at a basic, again, this is also extremely simplified, but at a very basic level for your structure, a set of inputs, a hidden layer, and a layer for your outputs. That input layer is literally just taking all your data and sending it into the net. The hidden layer is doing your processing, your computations. And each node on that hidden layer has an equation on it. And each of those nodes are unique. the weights are different on each of those nodes. You might not necessarily send all the same inputs into all the same nodes. And then each of those nodes will determine, based on the weights in them, based on the inputs, whether they're going to send a signal out and how many signals it'll send out. And then the output will combine whatever signals it receives and give you back a result. And that's your layered structure. Now, how many inputs, how many outputs, how many hidden nodes, varies based on the problem that you're trying to solve, and that's where you start getting kind of complex in terms of building out the structure. But where you can also get complex in terms of building out the structure is that you can layer it. You can have multiple hidden layers that are in your actual neural net. And all you're really doing is adding neural nets together. Your first hidden layer could suddenly become an input layer to the next hidden layer. And the next input layer can become an output layer to the previous hidden layer. And those hidden layers are allowing you to look at your data with more complexity and with more nuance in terms of the feature set that you're working with. But what does that mean? Well, let's take a computer vision example. You have, let's say, a neural net that you're trying to build out to predict, is this picture Ada Lovelace? And you have a set of pictures you're going to use. This is an example of one of them, let's say. And I've got sort of a loosely, imaged neural net above, but usually you'll have like thousands or you could even have billions of nodes in one layer. So you take a picture, you break it down into pixels. You have however many pixels that you're going to process. Those pixels are converted to numbers. The numbers are going to represent how dark or how light that pixel is. And then those pixels become inputs to the first layer. And the first layer, each node could start to look at certain edges. Because as humans tend to see edges when we look at objects. And interestingly enough, neural nets, some of the first layers when they're doing computer vision also see edges. So one node can look at like an edge of an eye or an edge of a nose. Another node could look at a different type of edge of an eye. Based on this picture and the way the pixels are numbered, will determine which nodes are going to fire. Based on the ones that fire and they send inputs to the next layer, that layer could be focused on objects and interpreting data about maybe somebody's nose or eye or lips. And then based on that picture and which nose, eye, or lips fires, that will become input to the next layer, which could have each neuron focused on a facial type. And that face type, whichever inputs it gets, will determine what's going to fire and send out an actual prediction or classification. Now in this case, I've got an inaccurate classification. And I did this on purpose because in order to actually get your neural net to work, you're going to have to spend some time typically training it. Some of the most successful neural nets we have out there are typically built with supervised learning. And just to really briefly touch on this, supervised learning is basically labeled data. It's using labeled data to build the model. And the way we would do this in this case is we'd have a set of pictures that are labeled, and we'd split them up into a test set and a training set, and we do cross-validation to help make sure that the model is working the way we want it to. And the way we would do that is because when you run the actual neural net, when you're training it, you're going to kind of build out your structure, you'll have some idea, and there's a lot of work that's already been out there that will help give you some idea of how many nodes to build out, and then you'll do maybe some random initialization of weights, and run through the photos and come out to the end with classifications on your photos, and then you'll have labels to compare them to. And you'll use a loss function. And a loss function basically is going to take the data that comes out, compare it to the actual labels, and come back with an error value. Again, there's multiple different types of loss functions. I've listed just a few up here, but I'm mostly wanting you to take away with the idea that loss function helps you determine what your error looks like. And the reason why you want to know this is because then you're going to use an optimization method. Sometimes, and a lot of people tend to use something like stochastic gradient descent, but you'll use an optimization function or an optimization method to take the loss function result and move back into the neural net and update your weights, your coefficients. We're coming back to the idea of this line that I mentioned to start with. You're taking this neural net, similar to what I was saying about linear regression, and you're going to take the data at the end and then go back and wiggle the weights on each neuron. And that optimization method will tell you how to wiggle the weights. The loss function will tell you kind of at what value you should wiggle those weights. It's a lot of information. But what I'm trying to get across is some fundamentals that you can build off of to help move forward with further doing work and research around neural nets. You have your input layers, you have your hidden layers, you have your output layers. Each neuron in a hidden layer is doing some type of computation. They're unique. The weights are your coefficients. You're using some type of activation function in each neuron to determine is it sending a signal or not. And when you get to the end, you're comparing what you predicted with what you actually have to get what the loss is, and then using an optimization function to go back and update. And you'll just keep doing this and training this until the error rate stops changing. Hopefully it's gotten as low as you would like it to get, and if it hasn't, there's probably some other things you need to do to tune it. But you'll literally just train. Keep going through it and training. Once you're done, then you can go back and you can do validation, and you can take the test set that you set aside, run it through, come back and see how accurate is this neural net, or have I overfit it. There's a number of other things that can be done here. You might have to do regularization and stuff, but as I mentioned, I just want to give you at least some basics to understand what a neural net looks like. All right, a couple other things I want to make sure you understand walking away from this talk. There are different neural net types. I gave you the basic structure, which is that, linear kind of feed-forward structure. That's one where you literally are going to pass the data straight through in terms of the layers and how they're stacked. There are other types of structures, and there are a lot of other types of structures, but just to give you a sense of what that means to have different types, I have a recurrent neural net, and what that means is that when certain nodes fire, it might loop data back into the neural net to earlier nodes or to itself as an input. Recurrent neural nets are really great when it comes to natural language processing based on the order of words in a sentence and trying to interpret what that means and how to process that, or speech recognition. So this is a different type of structure that you would want to take into consideration when you're looking at neural nets. And then the other one that I have listed up there is convolutional neural nets. And the reason why I've listed that one, and I'm not going to explain how this structure works, but whenever you hear about neural nets and you hear about deep learning especially, you'll typically hear about convolutional neural nets, and they're fantastic at image processing. So just be aware of that term, and then I would recommend looking into it further. They're also extremely good at scaling. But as I mentioned, there's a number of other types. There's like deep belief and autoencoders, and these are all things that there's a significant amount of documentation out there that you can dive into and better understand. And another point that I want to make sure I cover is that if you really want to get serious about launching your own neural net, you should spend some time understanding certain systems concepts. And one in particular is graphical processing units. I know all of you have CPUs in your computer that do the processing for your computer. And I'm sure all of you also have GPUs in your computer that do graphical processing. But you probably don't have necessarily the GPUs that are on the market we're typically using for neural nets. GPUs, at the end of the day, it's a much faster way to process data. It's highly valued when it comes to doing research and gaming. It's just extremely faster than any CPU that's out there. Some might debate this a little bit, but for the most part, GPUs are valued because neural nets can get really complex very fast and take a lot of time to train, and you want to improve the latency, the amount of time to build and get that neural net working right. So you should spend some time understanding how to use a GPU. I've mentioned some other areas if you want to go even further beyond just one single computer that you should potentially look into to get serious about launching a neural net for real-world applications. I'll let you investigate that further when you have time. All right. Okay, so you don't have to go out and learn about calculus and linear algebra and systems engineering to get started. There's a number of Python packages that can allow you to kind of get up and going on your own in the near term. I've tried to give you a sense of kind of how much more hands-on you have to be with the different packages, but it varies. The main thing I want to mention here, Theano, it's fantastic. It's well-researched, well-documented. It's also going to be the most kind of bare bones in terms of requiring you to really code your own layers and code your, really understand the equation that's behind, or the equations that are being used in the neural net structure. I've mentioned a bunch of machine learning packages that I've come across that many of them are actually built off of Theano. They have different ways that you use them. They also have pretty solid integration. Some of them have some pretty solid integration into GPUs, or an easy way to spin up a GPU with them. Cafe CXNet, those are ones that are actually C-based libraries that have Python bindings. And GraphLab and Scikit-learn, machine learning libraries that are actually kind of the most abstract, meaning you really need to know the least about a neural net to really get those spun up. Whereas MetaMind is more GUI-based, it has a Python API, and you mostly just need to give it data and give it some of the parameters, and it'll run a neural net for you. So at least these are some of the ones that are out there. I can't necessarily attest to how good all of them are, but you can play around with them and see. So for today, I wanted to at least give you one example. And we're going to use the MNIST, which is a pretty popular data set because it's considered the hello world of neural nets if you're going to get started. You may have already seen this before if you've played with them. But what you're doing in the MNIST is you are classifying images of handwritten digits between 0 and 9. And so to do that, kind of going back to what I was talking about before, you're going to take an image, you're going to break it down into pixels, and you're going to change those pixels to numbers based on how dark or light. I've oversimplified this here just to really emphasize the point, but it's actually the numbers are typically 0 through 255. The structure you're going to create with your code is you're going to take the image as an input. The image is 28 by 28 pixels, so it's 784 input nodes. You'll create your layers. You could actually just have one layer with this problem set, but I just went ahead with a couple of layers to kind of reemphasize a couple of other points. You could have up to, let's say, 1,000 nodes in one layer. And the output nodes, you'll notice we're trying to classify between 0 and 9. So you're going to have one node per classification. And each node is going to be like an on or an off or some type of percentage on how much is that picture that number. The code. It's really going to be this simple when you're working with GraphLab. I don't work for them, but I just wanted to give you guys something that felt like, hey, I could literally spin this up in the next few minutes if I wanted to. All you have to do, you import GraphLab. You also do need a product key to get it running, and you don't have to pay for it to play around with it. But you start out with GraphLab. There's a link that you can use to import the actual data set. The data set is 2 columns. Each row is representing an image. And the first column is just the list of numbers for each of those pixels. The second column is what the actual label is for that data set, or for that number. You import that as a data frame. That's what an S frame is. And you then literally call GraphLab's neural net classifier and use the create method, pass in that input data frame, and tell the create method which column has the actual labels. And it will spin up a model. It will automate a lot of other things for you. Spin up a model, leverage that target, and use that to help train. It has a lot of things pre-baked. You can investigate in the documentation what's been pre-baked, and you can also find there are a number of other parameters you can use here to help tweak and adjust and change the neural net in the ways you want to. But it'll do a number of things for you, as I've said. And once you're done, you've got a model. And yes, this is reversed. I'm not going to explain why. But you have an input picture. It will create these different layers, and it'll do the interpretation for you. And you can pass in a new picture it's never seen before, and it'll come back with what it thinks that number is. As long as it's something 0 through 9, and if it's not, could be interesting to play with anyways. This is from Jan LeCun's site, and he built the Linnet back in the 90s, which is what this is all kind of based off of. So you can check that out if you want to after the talk. So once you've got your model, one of the things that GraphLab provides is an evaluation function, and you can take a test data set that you haven't used so far, run it through the evaluation function to find out how good is this neural net. And in this case, it's really saying, based on the number of values it comes back with, how many were correct out of the total that it looked at. And the accuracy score is actually pretty good for it coming pre-baked. And granted, this is a model that it's worked with before. So you can use this to start kind of playing around with your own data sets. You can go find new images and sort of start tweaking the model itself. Or you can explore some of the other packages that I mentioned. And since I didn't have a lot of time to go through as much code as I would have liked, I actually created a repository where I have some of the packages I've mentioned, not all of them, but some of them with the MNIST examples that you can reference. And I've done some adjustments to the code so you can look at that and see how that works. And that's already out there that you're welcome to look at. And if you want to add anything to it, please feel free. A couple other things I want to kind of touch on before I wrap up. Deep learning. So deep learning, it's not just every neural net structure out there. It does typically have more than one hidden layer in it. But that's not why it's deep. Why it's deep is because it does automatic feature detection. Unfortunately, I don't have a ton of time to explain what is automatic feature detection, but I will say this. To build really good models, we spend a ton of time and money to actually get great features, and it's types of data. It's things like, if you look at your user base, their behaviors or their demographics, do they click on something or not? Are they female and from, North America? Those can be features. And with deep learning, you can spend a lot of time and money, basically, like I said, trying to find good features that will give you good models. But deep learning is really great for finding automatically finding features. And I would just stress that if you want to understand this further, I would dive into that space and really learn about what feature engineering is. So I have a number of resources that I came across that I felt were the easiest to work with when I first started putting together this talk, and I curated a little bit of that list here. But I have a number of people who helped me with this, and I'm very grateful for. And I have a number of other references that I've included that will all be posted so that you can use this should you decide to investigate neural nets further. Last couple things I want to make sure I touch on. So in the near term, neural nets are going to be the most beneficial, like I said, in feature engineering, but they're also going to be really valuable when it comes to combining different types of neural nets. There was recently a lot of research done and some fantastic findings that came out in the fall from like Facebook and Stanford and Google and so forth around combining convolutional neural nets with recurrent neural nets to do automatic feature tagging or descriptions. The areas that I mentioned earlier on, like natural language processing, computer vision, these are areas we're going to see a lot more advancement. We have so much more room to grow, and neural nets are going to play a significant role in that. In the long term, and this is why I think a number of the experts and others are in this space and learning about neural nets, it's really going to be exciting what we can do with unlabeled data. I've talked a lot about labeled data, but the potential for finding patterns and what those patterns might mean in unlabeled data, or even using labeled data and finding new patterns that are beyond the bias that we're applying to it, are pretty exciting. Having a neural net be able to come up with some kind of new ideas that you'd never thought of before. And yes, this is verging on AI. Neural nets play a large role in the AI research. When I was doing this talk, and I was practicing this talk at home, I had my iPhone plugged into the wall. And Siri kept piping up and trying to search for things, which was not extremely helpful. But I kept thinking, it would have been great, and yes, I'm one of those who's a big sci-fi fan, that if Siri could have actually listened to me do my talk and given me feedback. I think those are the things that we could definitely see come about with neural nets. It's scary, sure, we have the potential for HAL, but I actually like to believe that we have some pretty amazing potential with neural nets. And that's why I find them interesting to continue to research. And if you do too, I would just recommend kind of don't let this feel too overwhelming. Look at this as a way to start building on top of it and dive into the space. That is pretty much what I have to share. I just wanted to say a couple of other things that, one, I'm really grateful to the Python Software Foundation, also to PyLadies, and give a shout out to the HackBright women who are in the audience and the PyLadies women in the audience. And one thing too, at lunch, I learned that there are no core contributors that are women for Python. So any women out there, please, jump in. I'd love to hear about core contributors that, feel free to get into it. So yeah, that's all I got. Thank you very much.
Is this on? How to do this? Is this mic on? Okay, good. So we have about 1 minute for questions. I ask that you come to the mic if you have a quick question.
Hi there.
Hi.
Yeah, most of the tasks you talked about were sort of classification tasks. Could you talk more about, do you have anywhere that we could look if we wanted to use neural nets for regression? Is this a good idea, bad idea?
Great question. I would need to look and see in terms of the references that I pulled so far. I don't have anything that's coming to me off the top of my head, so I'm happy to talk to you afterwards, though.
Do any of the neural nets that you mentioned most closely approximate human neural functioning, or is human neural functioning kind of a composite of some of the different ones that you mentioned?
So we're still definitely trying to understand the brain and how it functions, and neural nets are very far off from really fully investigating that, but there are a segment of researchers that are very much interested in biological neural net functionality and are pursuing it. HEB in particular is always referenced in terms of like approaches to research around, and I think that might be the time, but in terms of specific ones, I don't have them off the top of my head, but there are definitely neural nets that are specifically focused towards more mimicking the actual brain functionality.
So just in case you didn't hear that, the session's over. I want to thank you for coming and give a round of applause for Melanie.